Hello everybody. My name is Ashkan Borna. The title of my talk is The Path Toward Energy Efficient Inference Engine Architectures on Scaled and Beyond-CMOS Fabrics. This work is a collaboration between ECS Department and Redwood Center for Theoretical Neuroscience at UC Berkeley under Sonic program. So why Neuro-Inspired information processing? So traditional semiconductor scaling is slowing down since energy, low signal to noise ratio, and increasing variability of scale devices are limiting the scaling. So meanwhile, looking into neural systems, what one could see that a system with potential problems that has a noisy variable devices, yet it managed to have a stable and robust answer. So although that the brain is so complicated and there are vast amount of unknown parameters in the system that it doesn't sound logical to copy the system. But one still can, by looking into the system, can get some basic ideas of the property of how it doing this function. So we can see that this is massively parallel with high density. It's using the over-representation and redundancy and learn and adaptivity to have a very robust answer. And also the signal representation is changing in different parts of the system. So by looking into the system and looking on our own library of devices we have and the state variables that we choose to represent our signal, the type of data representation we want to have for our signal, and also the architectures, we might be able to tackle some of these scaling issues for the upcoming devices. So the traditional computational platforms are based on deterministic algorithm and architectures. And since the scaling devices are becoming more and more noisy and statistical, the mapping between these two is becoming very hard and also inefficient in terms of energy. Whereas for the statistical computation, there might be potential benefit for actually having a noisy devices. So of course, we can't have all the application we want and improve based on this statistical computational platforms. For example, you can't probably design a GSM amplifier and that meet the specs and still have a statistical platform. But there are a vast amount of applications, for example, feature extraction, classification, recognition, and learning, decision making that fall into this category that might be helpful for upcoming devices. So what are the metrics? So the metrics for these Neuro-Inspired algorithms are more or less similar to the traditional ones. However, because the representation of the signal might be changing, we might have to redefine some of the metrics. But at the end of the day, the things that are very important for especially these applications are performance, and most important is latency, because you want to be able to, you have a vast amount of data and they are noisy, and you want to be able to have a very fast decision based on upcoming data. Also the power, which is always the case, we are always limited in terms of the power. Robustness, and it comes in two different factors. For example, first you want to have the robustness of the system performance with regard to its devices that are noisy and variable. Also, your incoming signals that might be very noisy. You might have a very noisy input signal, and you want to have a robust answer even for noisy signals. And also the density. So because our envisioned implementation is going to be 3D structures, we can't talk about area anymore. So we have to talk about density. So the dimension of the representation is that when you have a signal, and we can say the representation is minimal if the dimensionality that we choose is just sufficient enough to represent the full coverage of the signal. And the representation will be hyperdimension if the number of the dimension is by far more than the required, and that will give you a lot of redundancy. So what are the basically property of this hyperspace? So if you pick a point in this hyperspace and calculate the distance of the other points relative to that point, n is the number of the dimension in this hyperspace, k is the Hamming distance to your picked to your desired point, and p and q are the probability of being 0 and 1. Let's for now assume that they are both 0.5. So it turns out that this is a binomial distribution, and if the n is large enough, you can just approximate it with a Gaussian. And what you see is that whatever point you pick in this space, most of the space is just extremely clustered and is about half of the space away from your desired point. So in other words, if you pick a random point, then it has a specific property. And you pick another random point, the probability that that point is close to your point is extremely low. And it just, most of the time, it's just going to be half from your desired point. And this clustering would give you a lot of robustness for lots of these recognition tasks. So the question is that if you want to design the physical platform for this, is that, so you of course you don't have the unlimited factor for choosing this hyperspace. So you want to know what is the minimum amount of the hyperdimension I can afford to have. And the answer is about the SNR. SNR is a limiting factor. For example, in this case, what we see is that we have 10 patterns in our library, and we want to recover the desired signal. And if my patterns are, for example, in this case, are 1,000 bits or 10,000 bits, then when my desired signal are stored in the pattern, I get a high SNR. And when it's not, the noise response is very, very low. So I get a very good high SNR. But if I just reduce it to 100 bit, I can see that the SNR of my systems is becoming to be low and low in this case, like around 2 to 3 dB. So the fundamental question is that it depends on your application. So you have to choose your application, you have to choose your bit fidelity, and based on that, you quite clearly know the SNR and the number of the amount of hyperdimension you need. And also, one interesting thing about this is that the way you can think about it is it's like an integration in time. You're doing it in space. For example, if you have an integrator and you have a noisy input, you have an input, but it's buried in noise. You can wait long enough in integration, and since your noise is coherent and the noise is, your signal is coherent and the noise is the average is 0, you'll get your signal out of this noise after a certain time. So same thing is here. You can just do it in overdimension, and what you buy is that you don't need memory for that. So one of the systems that we're trying to develop based on this hyperdimensional representation is sparse distributed memory. The inventor of the sparse distributed memory is Pentti Kanerva. He's in Redwood Theoretical Neuroscience. And this system actually worked based on this hyperdimensional idea, and it actually can be used for lots of this pattern recognition, classification, and tasks in this realm. If you take a look at the architecture and compare it to typical RAM, you see some of the similarity. So for example, in RAM, you have address register, and you have word in register and word out register. And if your address register is 20 bits, you have 2 to the power of 20 bits in the physical address in your address matrix and also content matrix. But in SDM, what you have is that you have, for example, 1,000 bits, or even more or less. So it's impossible to have one-to-one correspondence with a 2 to the power of 1,000. So what you're going to end up is that you're just going to pick a small version. For example, let's say I put 1,000,000. So then I know that each time I have an input address, the probability that I'm going to match exactly to that address is extremely low, that I need to define a radius of the Hamming distance, that how close is that address to the close by neighbors. And based on that, based on the distance, I can actually start to activate that corresponding rows and start to write in the content matrix in order to basically learn those adaptations. So it's like that. If these are correspond to your physical address, you have your input address is the chance that your input address is going to fit on top of one of those is extremely low. So you have to define some radius, and you pick these, and you pick all of them, and when you're reading, you will just sum them up, and then do a thresholding. And when you're writing, you just write in those multiple locations. So what you will gain based on that is you will gain a very robust pattern recognition system. So if you want to design this system, the fundamental question you need to ask yourself as a designer is that, okay, how many number of the rows I can choose? And also, how many patterns I can save, and how many patterns I can very robustly clarify, and also about bit fidelity. So based on the two main basic operation of this system is that first you have to train your system. You have 3 different patterns. You will start to change the content of that address matrix, of the content matrix based on those patterns. And then when you read, you will retrieve that signal and compare it to this originally stored version and take a look at the discrepancy. So if you do the math through the operation, you will see that if you require certain fidelity, based on that, you will get this gamma. And the gamma is actually the ratio between the stored patterns to the physical address. So if you can think of T as the number of the stored patterns, and M is the number of physical address, and the ratio you want it to be 1 ideally, but it depends on the bit fidelity you require, it will change. And then based on these two numbers, you can set the radius of activation that we talked about. So what we see here is that if your application requires a very, very high bit fidelity and basically fall in this range, you will see that basically it's not the best idea to move to this sparse distributed memory, because then practically the ratio of your patterns to your physical address is becoming to be 0. But if your application requires the bit fidelity lower than, let's say, 0.99 or even 0.9, then you can actually use more than half of your actual physical address for pattern recognition. The other question that is very important is that how you want to implement the content matrix. And the reason is that, just imagine I have 1,000,000 row here, for example, and I have 1,000 bits, and I have 1,000 bits for my wording register, and each of these, I don't know, might require a couple of bits to represent. We want to count them and count up. So the area is becoming really important. So you want to know if you want to do it digitally or analog, what's the ratio you need. And so we did the calculation, and it turns out that you can actually, for the counter limit, number of 5 is enough. And if you go to the analog, the very lowest NR is still good enough for implementation. So then what we did is that we start to take a look at the application for implementation in terms of the CMOS, and it turns out that it's just actually the area is going to be tremendous. So it's not a good idea to use it with CMOS. So what we're going to do is implement part of it in the you can have an address matrix and the Hamming distance calculator in the CMOS, but the rest, for the content matrix, you need to have memory store technology. I think I'm running out of time, so I'm going to skip this thing. So what we'll do is this is a collaboration with Stanford, Professor Wang and Mitra, is that we were having these RRAMs to basically first store this content matrix for us. And the other thing that it can do is you can actually use the RRAM and inverters to map, to have your signal and distribute that into hyperdimensional representation based on the randomness. You're exploiting the randomness of the content of these RRAMs. So in conclusion is that the need for defect-tolerant hardware to noisy nanometer scale device is rising, and there are a large class of application that actually you can use for in recognition and synthesis and mining, that actually you can actually exploit this statistical instead of just fighting them. And deploying the heterogeneous system is a must if you want to meet the required specs of area, power, and etc. And also, before getting these devices in the massive numbers, emulating these algorithms on FPGAs and GPUs is a good option to order to clearly analyze it, because simulation is just going to take a lot of time. Thank you.
Thank you, Ashkan. Questions? Yes, Eli? Get the microphone, please.
So there is some type of mathematical trick. I mean, we've heard of associative memory in the past, but you have some type of mathematical trick for taking advantage of sparseness. I know it's hard to explain these things, but can you give a shot at it?
So the mathematical trick is that basically there was a specific trick. What it was is that you actually you assume you have some Gaussian profile for your distance. So you pick these two numbers, and you have a tail of the overlap percentage of these two different vectors. And based on that tail, and assuming you avoid Gaussian noise, you can calculate the probability of the error of going to that tail. And based on that and bit fidelity, you can actually calculate the what is actually should be the required number of the hyperspace to minimize that beneath your fidelity. And then that would set your either, if your physical address is set, that will set the maximum number of patterns you can store, or if that is set, if you want to have a specific number of patterns, then that will set your minimum physical address you need to address that.
Questions? Yes, question there.
Have you considered using, I just went to a talk by Jeff Dean from Google, and they use location-dependent hash coding to do like cross products or, in an approximate way. And I would think in this sparse memory using hash coding to get you, so you don't have to look through so much. Have you looked into those kinds of things?
Not at the moment, but what we're really struggling at the moment is to have manageable hardware, because it turns out that the area you need if you want to implement it on a silicon, even this one, is about 20 millimeter square. But if you use the RRAM, we will, at the moment our main focus is to how we can actually have manageable area and power. So that's basically the thing we're looking at most at the moment. But that's a good point. We'll look into it, things.
I guess if you go 3D in the third dimension, you don't have any problem with area.
Yep, that should be the case.
If not, let's no more further questions. Let's thank Ashkan again.